Hello everyone, it is April 22nd, 2025, and this is the bi-weekly libhal meeting. Alright, for the agenda today, we're just going to talk about a few things. For the most part, this is a lot of stuff that will be for libhal 5.0. A lot of changes. Originally, I did not plan on it being this many changes, but as we started figuring things out, we realized that there are things we should solve now, so it's not as much of a breaking change into the future. It's going to be a big refactor, unfortunately, but I think it's worth it. All right, so first thing to talk about, this is actually not a breaking change. It'd be like a new feature that we could add and start using now. I was thinking about ARM IRQs and how they are something that you have to build a constructor for. Like, you hold almost all drivers that use interrupts will hold an IRQ number or a set of them for whatever interrupt they're trying to manage. And they will enable them when they need to, and then when they're done, they will then go through and disable all of them. And because of this, people have to write destructors. And a design pattern that is highly encouraged in C++ and by the core guidelines, I believe, as well, is, or actually by Jason Turner, I know that for a fact, is that you should not be writing your destructor. If you would not have to write a destructor, you should, or you should omit doing that. It would be best if all of your objects automatically handle themselves, and they do so in a generic way, a generic and consistent way, so you can't accidentally make a mistake when you write your destructor. Having people write more of their own destructors is more places where they can make mistakes. So to consolidate all that complexity and all those things you have to remember, this object will exist at some point. I'll add an issue for it. Actually, I haven't done that yet. I forgot that I'd even had this idea until I looked back at the slides and the things I'd added on there. But yeah, this is the idea. So the IRQ handler would be some object where you can pass in IRQ number. I'm figuring out how we should do the addressing. But my hope is that if I can get you a unique handler per each one of the objects that exists, that rather than having the situation we have currently, where if a driver can support 3 ports of something, then you have to instantiate all 3 of their handler functions. Not the worst amount of memory cost, but still a memory cost. So that's a lot about that. Probably when we actually have it developed and it's working, we'll talk more about it then. All right. So next up is SmartRef for everything. Okay, so let me tell you what SmartRef is. So track pointer is out, SmartRef is in. I spent a lot of time kind of thinking about tracked pointer and what it kind of meant. And what I realized is that it was this overly complex thing for solving a problem that we already have a solution to. And I think what had kind of happened is that for so many years, I had come up with so many good techniques to get around needing memory allocation that I thought that I could utilize that idea literally everywhere. And yeah, static can just get you out of that spot. Global variables get you out of that spot. But to be honest, I hit the wall where I kind of started looking back at what I was doing and what would be required in order to uphold all of this. And there are 2 things that came up. One is that if you kind of stand back and look at my stack allocation for all objects idea, which I talked to some other people about, which I found a way to do that, it was like building a variant out of your stack, which was also not efficient in terms of memory usage at least. I also realized that when it came to tracked pointer, it only was complex for the use case of stack variables. If something's static or dynamic, we don't need a lot of information to know if that object should be destroyed or not, or repointed to. That's what ref counting is for. Actually, one thing that really struck me, and I couldn't really deny it, was that track pointer for static and dynamic objects has like almost no overhead. Like it's there was no extra pointers I had to track. It just kind of all just worked. I didn't need anything special. So out of that, I realized that I needed to just accept what stack objects are, what the stack is, and what a heap is, or basically what a dynamically allocated area is, and just use it. So SmartRef is a smart pointer that has reference semantics. It also dynamically allocates. And I'll go into a little bit of that while we go through our talk. So one thing about SmartRef is that it cannot be reassigned to point to something else, just like how references cannot be reassigned like pointers can be reassigned. It is never null pointer. That means that there aren't any APIs like reset or a default SmartRef. The reason for this is I find that once you have those APIs and they're available for people to use, you never know when you get a SmartRef if it's valid or not. So you have to check it. And I think that's kind of a pain. And I think even supporting the code to manage that is a pain and not like that useful. I thought more about smart pointers and how they really were semantically like pointers. And then I realized that I didn't want that. I didn't want a smart pointer. I wanted a SmartRef. I wanted a reference that was able to do dynamic memory handling. So that's where this came from. So it's not movable, but it can be copied. The reason why I am going the route, and I could be changed, like someone could convince me otherwise, but I don't want this object to be movable because I don't want there to be invalid instances of this object in any frame. By making it a copy always, you can access any one of the copies and it would all just work. I'd rather that be the case than be movable and then having to tell people how to manage working with movable, like moved from objects. We just don't have to deal with that anymore. It's always valid when you do the assignment operator. It's reference counted just like shared pointer. And that's all I can really say there. It uses an atomic integer in order to do shared pointer-like stuff or ref counting stuff. I understand that there are platforms that may not support atomic int, and I thought about it a bit, and I thought, okay, well, maybe AVR doesn't support atomic int because they don't have any way to, ints are 16 bits on AVR, and the registers are only 8 bits in size. Therefore, there's not really any mathematical operation you can do on that machine that like could store both sections of the, I believe that's the case. If it's not the case, then cool, we might be able to have atomic int. But in those cases, the way that you get around this is by using disable and enable interrupts. If you have an API or if you have a means to disable all interrupts and enable all interrupts, which I believe AVR, I'm certain AVR has provides this, then you have an atomic int. Yes, that sounds pretty awful, but again, I'm hoping that with our design principles that it bears no effect on the end result of the code. I guess I'll say one thing, which is that even though we're allowing dynamic memory allocation, it's only at initialization. So I'm going to talk about this more in the allocator section, or I guess I don't really talk about it too much, but I do want to bring that up now. I don't believe that we should be allowing dynamic memory allocation at runtime. We should use thread pools. We should use predefined memory for coroutines and all this other stuff like that. I think keeping everything fixed is a good idea, and then having requirements for how big something can be for whatever application has to be. Like your stack frame can only be this big and stuff like that. I think those are fine requirements to put on things. Yeah, so that's all I got to say there. Also, last thing about SmartRef is that it's optimized. I was looking through the design of shared pointer, and I was very disgusted with the GCC implementation. No offense. Just the the 3 virtual APIs and the 2 virtual destructors. One's the deleting destructor, was the other destructor. Now, if you know me, I love my virtual APIs. I think they're fantastic. I actually wouldn't even be, I think the problem, here's the big problem with shared pointer, is that you get a vtable instance for every single unique instance of shared pointer you create. Now, I think for the most part, the compiler was able to eliminate, I think I have LTO enabled, but it was able to eliminate all of the maybe vtables for abstract classes. But the vtables for the concrete classes, there were a lot of them. And for each unique one, there's a vtable, and it has 5 pointers in it, and you have each one of those be 5 separate functions. And I was seeing the cost of roundabout. I think I show about it later, but basically the cost was massive. I think it was getting towards 100 to 200 bytes per smart pointer unique template instance. Not good, not a good thing to deal with. So again, that's what I want to say on the bottom. I don't want Smart pointer, I want a smart reference. All right, so with that, let's talk about allocators. So I want to move libhal to the paradigm that Zig has, which is you have explicit allocators for everything. And the reason why is, honestly, the reason why we're moving to allocators is for flexibility and memory safety. Static can be forgotten, causing memory safety issues. Now, and this has happened a lot, you make your resource file and then you make things static and you forget to make the buffer that's going to be your received buffer also static. Now, I did come up with the idea that, what if we have like a static type that automatically makes the object that you put in there static, and then you make everything reference that? That could actually work. You could force everything to be statically allocated. But I have some concerns with this approach, mostly that it's not the most efficient in terms of your RAM allocation. Yeah. So here's the issue with having static types everywhere, and just using static in general, is there are situations where I believe wholeheartedly developers are going to want to make a change to what hardware they're using depending on stuff that's only knowable at runtime. Here's a very basic example. You have 3 pins and you have dip switches on them, and you set the dip switches for the type of hardware that's available on that particular board. Using those, you could read those things and then set your hardware appropriately. I think that's something that should be supportable. If you use static for everything, the static objects that do not get initialized still take up memory in your data or BSS section. They take up RAM. And they're kind of just dead there. They don't do anything of value, meaning that you have to pay the cost of not just the ROM necessary to hold all those, because you're going to need at some point in your code, you may choose to move from one case to the other case. You need to have all the code necessary in your flash to handle both cases, but it is a shame that we also have to do the same thing for RAM. I think that doesn't make sense. I think we can reduce the amount of RAM usage we have by utilizing explicit allocators. So that's why static, I still want to make this type. We're probably going to make this type, but it's not going to be used for this purpose. Another thing is automatic variable objects only exist for their scope, which is limited for drivers. That would require us to call deeper and deeper and deeper into functions in order to keep the objects that are on the stack alive. That's my stack allocation methodology I was talking about before. And the funny thing about this is that this ends up turning into dynamic memory allocation, or not dynamic memory allocation. Like, you can still figure out the maximum, but it's one of those things where like you won't break a build, I think, when you crash out your entire stack the way that you design everything. You won't, but you can use other tools to figure that out. But it's kind of like, it doesn't really give you, to me, I don't think it gives you a good picture of the amount of memory you're using if you try to keep everything on the stack. And this is where we go back to making sure all the allocators we use are statically allocated. That means we can know exactly which buffers are being used for what things at any time with a name and a label. So I think that's really powerful. So automatic variables only exist for their scope, and this is not the most, it's not a very efficient way to attempt to write in order to utilize RAM for all your objects. Dynamic objects are unbounded by lifetime scopes, and this lets the code decide. And I think the best solution that we have had when it comes to letting the code decide is, if there are any references to a thing, if there are none, then destroy the thing. If there are, then keep it around. This is how garbage collectors work. This is how shared pointer works. This is, I think, how we should do our things. You only use, only amount of memory is used for as long as it's needed. So to me, having allocators using static storage and a smart reference type that is non-nullable, it always points to something that's real, pretty much gives you lifetime memory safety. Now, obviously, there's things you can do that are memory unsafe, lifetime memory unsafe, and we'll talk about that in a sec. But I feel like this combination is what gets you to that memory safe point. All right. So what does this give us? Well, it gets us access to all the PMR types as first-class objects. The ones that would be of the most use to us would probably be like, well, we're going to make alternatives to this, but like vector. That could be one of them. Now, the PMR types don't usually give you enough information to be able to allocate all that you need. But the one benefit is if you were to make a mistake, well, overall, we have access to them. I don't know how much we're going to actually use them. There might be some cases where they become useful, but in general, I don't think they can be that useful. So maybe I should not have made this bullet. The next bullet would be enables the usage of coroutines with compact stack memory allocation. I've been thinking about coroutines and how we could support them in libhal. I have some ideas. We're not going to go over them today, but I have some ideas. And one of the things I wanted to consider is there's been a lot of talk in the C++ community and a lot of talk throughout different conversations I've had about coroutines being able to be inlined into the frame in which they are created in such a way that memory is actually like allocated on the stack. On the stack of the object that has a scope and access to the object, something along those lines. It's able to inline the information some way. I don't care about that option. People want it. I don't care about it. This is what you get from Rust. Rust gives you that. Rust does not always has a well-defined amount of information that it's going to allocate for any coroutine frame that's going to allocate. The reason why I don't care about that is Rust pays the consequences of this. You can't make anything that's async not knowable to the compiler. So like everything needs to be exposed and open in such a way that you could not really make a pre-built binary on this. Although I think they might have fixed that, so that might be a thing. But that was a problem. That's a thing that I don't think is fine. Whereas here we can have coroutines that are from virtual APIs. So you could dynamically call something that gives you back a coroutine. So what I think makes sense is with allocators, we get access to coroutines because they're going to need to allocate. Now, if we create statically backed buffers for each one of our different coroutine objects or coroutine tasks, the cool thing about how they go about allocating and deallocating, at least as far as I can tell, is that in general, for a starting coroutine, it'll allocate its memory frame that it needs to remember between each call. And then when you co-weight another thing, it'll allocate again. And if it co-weights again, it'll deeper, allocates again. But let's say that first one resolves. So then that one should then delete off its frame because the frames should be gone after that point. So we would delete off the memory that came before it. And then when that returns, we would go do the same thing again. Overall, this acts like a typical stack. It's like a stack within a stack, right? So with this stack within a stack type setup, when we allocate and deallocate, we never have fragmentation. So to that, I'm like, okay, well, if we ever exceed the coroutine's depth, we can throw an exception and then catch it. Kind of like how if you somehow broke your what's called the high watermark on a real-time operating system. This is the basically the boundary of how much memory you have, and if you exceed it somehow and the operating system is able to detect that, then it can intervene and do something. The thing about the high mark, though, is that it's usually too late by the time you've gone to reach out to it. It's damaged. Hopefully you had some extra padding at the end, which sometimes they'll do that to make sure you don't destroy something. But usually the operating system has to intervene and then look at it and go, okay, did they break past the barrier? Oh, no, they did. All right, something's very wrong. We need to call a handler for this. In our case, that memory safety issue would not exist. Our stack could still get overrun, but the memory allocator for the subroutines or the coroutines, those, the moment we try to allocate them, would tell us, hey, you can't allocate enough. So I think that's actually a pretty good thing. And I think that makes the allocations for this reasonable. So there still would be allocations happening, but they would be synonymous with allocating on the stack. And since we allow stack to be allocated, I think this works out just fine. I think if we can come up with tools to tell us after linking how big those coroutines are and like find the causal connections between them, figure out the maximum depth. If we could do that like we do with stacks, I think we would be in a good spot when it comes to coroutines, and then we wouldn't have to worry about running out of memory or even having the termination occur. Again, it enables smart pointers. So allocators enable that. We need that for lifetime safety. So yeah, it's good. All right, allows easy runtime decision making, for which driver you want to use. So for example, if you have some runtime mode between realizing, oh, we can either do bitbang I2C for something, or we can do native I2C. And this could be like some way to check this thing at like runtime, just to be able to, experiment things. This just gives us a lot more freedom. Using static would result in both objects being allocated in the data or BSS section. I talked about this before. And using stack would allocate the union of both and doesn't allow returning via interface pointer. So yeah. And unlike static, which easily allows resources to be cleaned up and reset. So unlike static, using a smart pointer allows you to easily, I kind of wrote this really badly, but basically allows you to clean up and reset objects. I'm trying to remember how I'm supposed to say this. Basically, what I'm saying is, with static, if you wanted to, well, one, you can't really release those resources from static objects because you don't really know what their order is. So it's not like you could get like a contiguous block of them. But if you wanted to reset a static object, you would have to call this destructor directly and then placement new on top of the old memory. It's a way to do it. I've done it before to bypass certain like annoyances with other projects in the past. But it's kind of a nasty trick. Fully safe though, fully well defined, but it's still something that we don't want people doing on a norm just to be able to get a very specific bit of behavior. I think we can just give that to them and then be better off all the wilder. Yeah, and also using an allocator can save RAM over other options. Like I said, these unions and like the extra memory that's kind of wasted, I think literally using a block of memory to just allocate all of our objects into is going to save us memory in the future. Even though all the machinery to make all that stuff work does cost us, which is what this next part is. So I've been looking at the standard polymorphic allocator, and it shows that the new and delete allocators are forced in. This is really annoying. I was able to reduce a lot of the cost from this by setting the new and delete to empty stubs to reduce code size. So yeah, I basically just made empty implementations for operator new and all the different variants of operator new in order to like reduce the code size. I was able to cut down the code size by 1 kilobyte from doing that. I think it was 1 kilobyte. No, I think it was more than that actually. I think it was maybe 4 kilobytes. It was a lot. And it made me realize that it might be a good idea to give the option to pull in a library that has those strong references built up. So when you call global new, it throws bad alloc, and when you call delete, it does nothing. And then if you needed a version that actually used malloc, then you could just not use that library. Or if you needed an option in Conan, we could like give you that option, default, and maybe our own versions and stuff like that, if you need it for some library that's going to use it. Yeah, and then another thing was I was playing around with the shared pointer. I already talked about the code bloat with it, all the template instantiations. 200 bytes, 100 to 200 bytes of code bloat. I saw in a couple examples. And then I'm still investigating where code size can be trimmed. There's another thing that I've spotted, which is that, and this is something that I should have noticed before, but haven't been keeping as much track of the numbers. I haven't really been caring about the numbers for how big our objects or demos are getting because I'm loading them full of a whole bunch of drivers. But I did notice string formatting stuff in the code base as well as standard string being brought in. And it has to do with the .at API for array and for mostly just for array and span. And the problem is that it's doing this string formatting so that when it throws logical error, which comes from out of range or out of bounds error, out of range I think it's called, it wants to show you the index you chose and the size that your object was so you can have a better diagnostic. I think that's great, and I think that's super useful for like just typical C++ programs written on like laptops. But that's too much. That is too much cost for me. That's actually really gross amount of cost for this thing. I don't want them to change. I don't want GCC to change their standard library. Maybe ARM's new lib stuff should do that. I gotta also make sure that I'm not seeing what I'm getting from pico-libc before I start calling out GCC. I could be wrong there. I also just realized that I should be do not disturb on Discord so we don't get those sounds. Give me one sec. Professionalism is awful. Do not disturb. All right, so yes, so I am, where are we? Yeah, so I'm still investigating the different sizes, that the different areas of the code base that can be minimized. All I know, though, is that the next part we're going to talk about how we're going to, well, vendor a lot of our stuff, but we'll get to that in a sec. All right, so with all these changes with allocators, there's going to be a new style guide. Really, it's a new safety guide. I actually called it a safety guide. I changed it around a couple times. Basically, it's our new safety guide. So here's what I want to become forbidden in libhal. So forbidden is the use of global new and delete, just because we're going to set them to nothing, and then you're going to explicitly use your allocators wherever possible. One other thing, I did not list this down, but I should have. The allocators will use PMR, C++ PMR allocators, and if a memory allocator were to run out of memory, they must use the null reference or the null resource, basically, which just throws an exception anytime you try to access it. That way, the moment you run out of memory, it just throws. We might just make our own monotonic memory allocator for that exact purpose, so that we don't need to have extra like pointers to things that we don't need. I'm looking into that. I'm hoping that's going to be possible without leaking and pulling in all the other objects, but we'll see. Right now, it doesn't look good. But yeah, so that's another thing. So no use of global new and delete. No passing by pointer. You can pass things as pointers to APIs that take pointers because we can't stop that. But no libhal code should ever be written with an API that accepts a pointer. Yes, pretty much. I don't think there's really ever a case where we actually need to send a pointer versus a reference. All right, so capturing a reference's address in a member variable from a function's input. So what this is basically saying is that if you pass by reference to something like some API of an object or the constructor of an object, it is not allowed to store the address of that reference inside itself, either as its own internal reference, which you can do at construction, or as some internal pointer, which we're going to soon ban pointers in as member variables anyway. So like that comes with the, should put that down as well. We're banning pointers members variables as well because we have smart ref instead. Much better. Yeah, so that's pretty much how that works. And then also storing a reference address in a scope above the current or some other unknown scope. So if you pass let's say you got passed a reference into your function, you have a factory function, and you pass that, and we have examples of this in the next slide. You pass that to some other object that gets returned. That is considered sneaking it out into a higher scope. Now, you are allowed to return the reference back out the scope. You got it from that scope, you can return it back to that scope. That is fine. But you cannot sneak it into another. So basically, that object's also breaking the rule right above it, which is capturing. If it was capturing, it was already breaking the rule. I guess I don't really need this rule anymore because, actually, the reason why we have this rule is that you can't set static variables equal to a reference, and also you can't set something dynamic. You can't pass it to something that's dynamically allocated. Yeah, that's pretty much the idea. So unknown scope would be dynamic, or static would be for the other case. Technically, if you were to capture it and bring it up, but that would be already handled here. Also, want to mention that this is basically, I think if I'm not wrong, Herb Sutter's idea of, is not entirely, this is not exactly his idea. His has like a lot more formalism to it. But this is my distilled version of it that will work for libhal. Because if you really, in my opinion, I think if you follow these rules, we really can't get into a lifetime memory safety issue. There's still bounds memory safety issues, and I have examples for how we might be able to get around that, but that's the thing. All right, so that's pretty much all the forbiddens, most of the forbiddens. So things that you should do: use pass by reference to indicate that a function only uses an object temporarily. So when you pass an object to a function by reference, that function has the opportunity to do whatever it can with that reference, up to things that are reasonable. Can't call delete on a reference, so that's another cool thing. And it's allowed to either return that reference back out or just do nothing. Just kind of just do nothing with it. Yes, that's pretty much it. To store and capture a reference to an object, the object must be a smart reference. This way, if you were to pass something as a smart reference, you get a copy of it. You get a copy of that reference so that you could all reference the same thing. And I am considering an object called a static reference, which is kind of like the static type I had before, which would be interconvertible with the smart ref. And the idea is that the static ref would always have a reference count of 1 because the object lives forever. So you can never really destroy it unless you explicitly called the destructor on it and did the kind of funky stuff we talked about before with placement new. So that's that one. And then all dynamic memory objects, including coroutines, should be stored in static memory. That way we don't have to worry about you dynamically allocating some memory and then that evaporating out of nowhere. And then buffers can be temporarily stored in an object for interrupts. So when I say buffers, I meant to say actually spans, to be more specific. I2C generally needs to store information inside of itself in such a way that its interrupts can find it. Usually we have a callback function that can capture up to 2 pointers worth of information. You can't pass the spans through this way, but you can pass yourself, your object self, as the context, and then store those buffers internally. I want to come up with a way that is consistent, because I don't really like this little extra kind of caveat because it makes everything else kind of impossible to follow. But at the very least, those objects within those member variables that store those parameters passed in, they should only be usable within the interrupt context that it belongs to and to the scope that it's within. But once you're outside of that, it should do nothing else. You should never access those objects. So coming up with a way to support that in an efficient way would be nice. So if anyone has any ideas, who's watching this currently, it'd be something to think about. All right, so a couple of things to go over. So this would be bad. You're passing by a pointer, otherwise pass by a reference. Good to go. And this should be both object, but whatever. You get the idea. No capturing, so you can't pass p int or p object, whatever, into this capture object, which captures it. That's not allowed. If you wanted to have a factory function, pass it in as a smart reference. I don't know why I put std here. It should be hal. But hal smart reference of the object copied in here, and it's all good to go. Also, if you wanted to eliminate a copy, you could pass this by reference. Because this ends up performing a copy, this is not capturing. That's pretty much it. It's not capturing. This will perform a copy, so this is all fine. Here, if you took something and then you took its address and you brought it out somewhere else, that's also unacceptable. And by extension, if this was a static variable in this scope, passing this into that static variable is also not acceptable. You're putting it into a lifetime. You're copying something into a lifetime that's infinite, and it's not going to work. All right, so with all the things I've been noticing a lot of code bloat and a lot of just the standard libraries. And I'm still currently we all still just use the GCC exception runtime. At some point, I'll move us over to Stell exceptions just because it'll reduce our code size by a good 4 kilobytes. And it basically just kind of falls in line with the allocator scheme because the my runtime uses a global allocator, or I'm sorry, not global allocator, gives you the ability to select an allocator for exceptions. And now that I think about it, I might make that, maybe I'll make that a requirement, that like it defaults to actually allocating nothing, and if you try to throw, it terminates. But if you want to actually throw, you need to set the allocator to something, and then when you throw, it'll allocate using that. And if that throws, then it figures out what it needs to do. Yeah, that sounds like a good idea. I mean, a reasonable idea, at least in my head. Yeah, so libhal needs an alternative to the STL and standard libraries because the offerings by GCC and Clang are bloaty and cumbersome to use. The cumbersome comes from the standard. There's things in the standard like optional. You can asterisk access it, and that is UB if it's an error, which I really hate. And it's bloaty. And this is for a lot of, like, some cases bad reasons, in some cases good reasons. Like the string formatting for your exceptions is, I think, useful for people. It's just not something that I think I want to have our code do. We don't do string formatting anywhere else in our libraries because that adds way too much code size, so we try to omit it. Also, we can make our containers and objects safe and compact. Yeah, so let's look at it. So we have a couple of ones we're going to do very likely, and then these other ones, maybe. Not sure if we have any real use case for them, but they might be useful if people really want them. So first off, we're going to go over optional. We can provide optional tref, just because we can implement it ourselves. It's not that hard to implement at all. Standard, I forget why we haven't implemented, like, I'm pretty sure it's in. I hope it's in. I don't remember, but I have to look into that. But basically, we can implement all the fun things that we wanted with optional T. When you use the asterisk operator, it does a bounds check. When you use the value function, it does a bounds check. All APIs are bounds checked. If you want to use the thing coming out of optional, you should copy it out. That's pretty much it. Taking refs out of it would be a bad idea. I guess taking the ref out of this guy, not just copying it into a T, would also break one of my rules, which is escaping a reference outside of the scope of something. I guess it technically doesn't matter because you're still within the valid scope of the object. That's how you got the reference. Sorry, going on a bit of a tangent there. But I want to make specializations for this for smart pointer. The reason why is Rust does this with its optional type. It will allow box and other types of pointer types to not have to require an additional like bool to represent if it's engaged or not. It can utilize things about the thing. For example, smart pointer is never allowed to be null. It is non-null by, I'm sorry, I said smart pointer should be smart ref. I don't know why I'm making all these mistakes with all these different values here. Sorry guys, I was a bit sleepy today. But smart ref is non-nullable. So in order to disengage it, optional T basically will blitz through the actual data of the object and just hard set it to 0. And by looking at the contents of the object and seeing that the values are, if you were to look at it byte by byte, is 0, then you can discern, okay, that object, that's not a real object. That's not something. So that's kind of the game plan. Some sort of basically type punning union where we can evaluate the inner objects, but just at a view, and we can use this kind of do some overt control. Obviously, this is unsafe, but we are basically wrapping our unsafe code around a safe shell, and we're making sure that there's no way to kind of leak out that safety. So that's what optional will get us. tref will be the same way in that it'll just use the null pointer value as a way to say it's not engaged, rather than using up an additional bool, which will inevitably cost us like 4 bytes because everything's word aligned. And I'm trying to think if there's anything else that might have a specialization. I had another idea for another specialization for optional of T. That would be just like this, but I cannot for the life of me remember. I'm actually going to scoot back real quick to see if I pick it up. Nope, cannot remember what it was meant for. Oh well, it must not matter. Cool. So now we have HAL array. Basically, we're going to remove the string formatting from the @API. That's all we're going to do there. We have dyn-array, which is basically like vector, except it only allocates once. It stays that way, and then you dispose of it after you're done with it. It has none of the APIs that would cause it to reallocate, which means that there's no index invalidation that can come from this thing. I'm sorry, iterator invalidation that can come from this thing. It's not really possible until the thing itself dies. It only requires 2 pointer sizes, or basically it needs a pointer and a size, and that's it. And then vector needs like a pointer, a size, and a capacity. So what we really just have is the capacity or the max size and then a pointer to it. More useful, circular buffer. We use circular buffers everywhere. This circular buffer would dynamically allocate the circular buffer memory. There would be no @API because it won't be necessary. The operator brackets has no preconditions, thus any and all possible inputs, it's going to take an unsigned value, are valid. Basically, we take your index and we do modular the size of it to get the real index. This way, if you wanted to keep a pointer to this thing, if you wanted to keep like an index to this thing and kind of always go forward, always be reading the next data going forward, you could. You just keep incrementing your number, and this will do the work of wrapping around. It has a bit of a cost, but looking through a circular buffer can have that kind of cost. It contains a push API, but does not contain a pop API, and the reason why is that, in my opinion, when it comes to circular buffers, especially if you want to have one manager and a lot of readers, and the readers are able to race with the circular buffer in a safe way, then all the other devices or all the other viewers of the circular buffer should have their own indexes into the circular buffer. They should keep their own read pointer and then look at the write pointer to understand where it's currently at.